and this interface should be, yeah.
Ho fatto partire la registrazione, quando ti senti puoi partire.
Ok, ma adesso non c'è nessuno in presenza. Okay, good. So welcome to the lab on kinematics and dynamics. So today the schedule is going to be, I'm going to give a small introduction about ROS first, for those who've never heard of it. Then I'm going to talk about another tool that we're going to use today, which is the rigid body dynamics library Pinocchio. And I'm just going to talk, I'm just going to mention what it is. And well, just let me ask you first if somebody had troubles with the virtual machine, because it's essential for this lab. In any case, if you had troubles, you can always send me an email, and we can troubleshoot anything. And hopefully, if you're not able to do the lab today, hopefully with the recording and the code that we'll be sharing, you should be able to reproduce what we do today. So let's start. So I'm gonna first talk about what ROS is. So ROS, it's the most widely used framework in robotics, middleware, sorry. And it's what middleware is basically a type of software to glue together different types of clients. So for example, ROS, the main two ROS clients that exist are in C++ and Python, but there are many. And it gives you this number of standards and interfaces that make easier for developers to just glue together different applications for different that require, for example, different execution times. And there are others such as JARP and Orocos. And why should we use ROS? Well, it's open source, and most of the robotics today, at least in the past 10 years, are based on ROS, and most of the research labs, they use ROS. It's very well maintained because there's a super large community developing for it and creating packages. As I mentioned, it's very large and very active as well. So there are lots of maintainers of different packages. Of course, there are packages that become abandoned through time because probably it was the project of a PhD that did it just to graduate, and then nobody took on the work of him. But most of the important libraries, they're very well maintained, and there are versions coming, new versions of the like new distributions of ROS coming every year. And as it in the same idea as Python, ROS makes prototyping and developing ideas much faster. And in fact, the main language in which ROS is developed, it's Python now. And C++ is used when you require a bit of higher performance. Although, in my own experience and now my lab experience, there are some drawbacks related to ROS. The main one that everybody complains about is that there are no real-time guarantees. So basically, I mean, although there are libraries that try to deal with this, like ROS control, in general, there's no deterministic time in ROS. So the time that we can measure in ROS, it's basically an approximation of the time. So, and when you're doing control, it's really important to be sure how much time everything takes, a process takes. Another thing is that, I mean, there's not an explicit dependence on a specific distro of Ubuntu for versions of ROS, but it doesn't work well. It doesn't pair up well with different. So for example, we're using ROS Kinetic with Ubuntu 16. If you go to ROS Indigo, then you would have to switch to Ubuntu 18, or you can make it run, but you always have this hassle. It's like having a gear that does not match very well. And going from one distro to another, for example, this is related to what I mentioned of the package that become abandoned. So somebody developed a package for Kinetic, but it never pushed the version for Indigo. So, I mean, this comes with it's a trade-off between having it to be open source and having the community collaborating to it. So you get really good things related to package development, but then maintenance becomes very difficult because it's such a large community. So the basic elements of ROS, I'm just going to give you a really broad overview just to go directly into the code. Nodes, which are basically executable files, are things that are able to run instructions, and they are mostly written in C++ and Python, although there are different clients. I'll talk about them later. There's also the master node, which is basically, we usually only call it master, but it's the main node, and it's basically the node that stores the information about the others. So every node queries the master if he wants to communicate to another. Then messages, it's a type of communication protocol between nodes. So you can define your standards through these messages files. We're not going to work too much on doing these things, but I wanted to give you an overview on how communication works in ROS. Then there's a topic, which is it's an asynchronous communication interface between nodes. So a node can publish or subscribe to a topic. I'll show you an example next. You'll understand this idea of publishing and subscribing a bit better later. There's also services, which is so a publish subscriber type of communication. The publisher, it's continuously sending information, and the subscribing, it's always like waiting for information, right? In a service, you request at a specific time, and then you need to wait for the reply. So there's always this synchrony between the nodes. And then this small drawing. So for example, a node published to a topic. I'll give you a specific example in the next slide. And then another node subscribes to this topic. I'll show you what a topic is. I'm putting links to documentation just so you can get an inner view of a deeper view of what each of these components are. So I'll put you a bit of an example of our own work. So what you see here, it's kind of the architecture that we're using now to do foothold adaptations in our quadruped robot. And this is just one small piece of all of what we do. So let me show you a video just that I can, just so you can get a better idea of what I mean. I will stop sharing and then Firefox, okay. Share. Okay, so basically what we did was that we trained a neural network to adapt the foothold locations of our robot while it was trotting in difficult terrain. Here you have our quadruped robot IQ going through a series of beams. Then we tried this on experiments. We tried to reproduce the scenario. Of course, we didn't have enough space to make it as large, and also the approach works under disturbances. So here, my colleague is pulling the robot to step over the gap, and then it comes back. Okay, so let me go back to the presentation. Okay, so the idea is that our robot IQ, it has different nodes. So the one that we're interested in is the robot state publisher node. So this is basically a node that gets the data from the process that is computing the states of the robot. So for example, we have a state estimator that gives us the X, Y, Z position in space of the robot, and then the roll pitch to angles and the Euler rates. So we send this to a topic called robot states. I'm just putting the topic here just to make it clear that it's a topic, but in the topic, it's just robot states. So we send a robot states message, and then the neural network, one of the inputs of the neural network, one of the many inputs of the neural networks are velocities, the current states of the robot, so that we can compute. It was trained to understand the velocity at which you're going, and then knowing where your body is going to be, you're going to step in a location that it's safe. So we train this neural network, and then we call this a CNN node. The CNN node computes the foothold correction. It senses to the foothold correction topic, and then this sends a foothold adaptation message to the well, it's not sending. It's basically the robot. The robot node. There's a different node here. It should be a different node here. Subscribes to the foothold adaptation message. And that foothold adaptation message goes into the control loop so that the robot changes the trajectory of its legs using the joint space controller. Okay. So this is just a small example. Then I talked about clients. So a ROS client, it's a collection of code to interface with the basic elements of ROS. So there are specific libraries in C++ and Python and other languages that are targeted to use the interfaces of ROS to handle the standards of communications of messages and services and topics. And this is called the client. And the main clients, as I've been saying all throughout the talk, there's a ROS CPP, which is the C++ client node, which is mainly for high performance applications. Then there's ROS Py, which is written in Python. It's the most developed one, and it's the most maintained as well. And then there's ROS Lisp. I recently heard about this. This is one of the main clients, but I've never heard of anybody using it. I've read that it's mainly used for planning. And there are also experimental clients. There's a MATLAB Simulink one. I've used it long ago when I was developing. Of course, MATLAB and Simulink are not suitable for performance on a real robot. Although, for example, the German space agencies, they use MATLAB, but they don't use ROS. But in general, MATLAB, it's not good when you're trying to implement something on a real robot, but it's really good when you want to prototype things, especially Simulink. It's a feature that I've not seen the same in any other type of software. Then there's also a Ruby one, an R one. There's also a Go, the language that Google developed, and there are many others. Then another open source tool that we're going to be using today, it's the Pinocchio library. And Pinocchio, it's basically a library that contains facilities to compute forward, inverse dynamics, forward, inverse kinematics, and their derivatives. And there are many of this, like RBDL. For example, in our lab, we use RobcoGen, which was developed by one of our colleagues, Marco Frigerio. And there's also KDL. So the software library, what's interesting about Pinocchio is that it's tailored for rigid body algorithms for multi-body systems. And there's another feature that I will mention later on. And as I mentioned, what we can compute with Pinocchio are forward kinematics, direct inverse dynamics, and their analytical derivatives. And this is the feature that I was mentioning. Because in general, now that optimization is becoming the standard for control, if you recall the lecture of well, when the professor introduced the optimization problems, one of the main features is that you basically need to get the gradient of an expression, and this gradient implies that you need to take the derivatives, and there's taking the derivatives of the dynamics equation. It's very time consuming, especially if you're doing finite differences. So one of the main features of Pinocchio is that it computes the analytical derivatives. So those are way faster because you already have, it's just basically evaluating an expression. And why are we going to use Pinocchio? The main reason why we're using is because we're gonna do a comparison of what we're gonna write manually the functions that we developed for kinematics and dynamics during the course, and we also use it for analysis. And well, I'm mentioning here that the main feature is the derivatives, the analytical derivatives, and as I mentioned, it's useful for optimization in general. We're not going to do this. Unfortunately, there's not enough time. probably in a later course, I think in the course of Andrea Del Prete, you do optimization-based control on robots. And well, you can do derivatives of the inverse dynamic, as I mentioned, using finite differences, but this is in general really slow. Another alternative is to use something called automatic differentiation, which takes advantages of the algorithmic structure of the problem, and it uses this to automatically generate code. So for example, this is what RobCogen does. So for example, automatic differentiation is faster than using the analytical derivatives of Pinocchio, but it requires a pre-step of generating the code. Whereas in Pinocchio, you don't need to do this pre-step. You can just basically adapt the library, and then once you have you can download the library, install it, and then you don't have to generate automatically the code. It computes the derivatives for any type of rigid body system, that like multi-body rigid body system that you can that you want to compute. So this was for the introduction. So let me stop sharing this screen, and then I will share this one. Let me allow me to share. All participants. Okay, good. So let me share my screen. So I'm going to share this. Okay, good. So you can all see the instructions for this lab today. So we're going to go through this. These instructions are already in the Dropbox folder. If I'm not mistaken, in the same one as the previous lab session. And so we're gonna go through three main topics in this lab. One, it's basically giving a very basic introduction on how to use ROS and how to visualize a robot model using the unified robot description format, the URDF. Then we want to compute and visualize the forward and inverse kinematics of a 4 degree of freedom serial manipulator. Sorry, yes, I jumped this one. So we're going to do the direct and inverse kinematics of the manipulator, and then we're also going to compute, analyze, and visualize the forward and inverse dynamics of this manipulator using the recursive Newton-Euler algorithm. This is one of two main algorithms that are used in robotics. The other one is the articulated body algorithm developed by Professor Featherstone. But this is let's say this is the precursor of the articulated body algorithm. Then we're going to be using the four main tools. The first one is Python. Oh, I jumped. I'm putting the links to the references in the footnotes of the instructions. We're going to use ROS, as I mentioned. We're going to use Pinocchio, and then we're going to use LocoSim, which is included in the Viltron machine. It's the library that Professor Focke developed. Is now in a testing stage for his courses. Hopefully, it can grow as a library that many people can use. So I already mentioned what we're going to do. So let's go through the preliminaries of this lab session. So I'm going to open the, how can I do this? Okay, let me do something just to have access to my, to the instructions while I'm here. Okay, labs. Okay, good. Okay, so if we are on the virtual machine, we put our, so how can I do this? Okay, let's go through the preliminary first. and then we will try to implement it. Okay. So first of all, we need to set up our environment to have the files for this lab, and I hope some of you are familiar with Git. In any case, Git is just a way it's a system to track changes within code, and it's a very well used tool in the programming community, and of course everything that involves code. It's just it's a version control software, and that's the word that I was looking. And basically it helps you to keep control on the versioning of code. So I created a what's called a branch, and then we with the files of this lab. So today we're going to use this branch. So if we go to our virtual machine, now let's type our password, which is student, for those who don't remember, the same as the username. And then we're gonna go through to a terminal. Let me open a new one so that you can see. So you can either open a terminal by hitting Control-Alt-T, or you can just click this icon here, which is the, I hope you can see my cursor. Yes, hopefully. And
yes, we can.
Sorry?
Yes, we can see your cursor.
Okay, good. So you can click the icon on the left. So let's type what's in the instructions. So first, let me go through them. Okay, so I'm gonna open a new terminal, so just so you can see from the very beginning what it's open. So I'm gonna make it a bit larger. Okay, so we go to the folder that where our Locosim library is. So we type CD, which stands for change directory, ROS workspace, source, which is abbreviated as SRC, Locosim. If you are doubtful on what the command is, but you remember the first two words, you can always just tab and it will autocomplete the command for you. Okay, so then we hit enter, and then this will send us to the right folder. Then we do git fetch to get all of the changes that we have on our repository. Okay, then we do git checkout lab_3, and then I was already on that branch. I'm just typing it, but you should see that you change to the right branch. Okay, then we do this. This is a module, and then it has several submodules. So to update whatever is inside of it, the submodules, we do git submodule update --init --recursive, and then this will update the submodules. I was already updated, so that's why no message appears. Then we go back to our ROS workspace folder. Okay, and we're going to run an instructions called cat-kinmake, which is basically the instruction that is used to compile ROS workspaces. If you want to read more about it, you can go to the ROS documentation. It's one of the first tutorials that you see. It's talking about the infrastructure of ROS, and then cat-kinmake. It's one of the main tools that it's used for compiling. Then we do cat-kinmake install. This is just going to create an install folder where our executables are going to be. So we do this, and then we get this. If you want to see again the commands that I typed, let me. Okay, here I am. Here are the commands that I typed. Cat-kinmake install, and then you should have the compilation. Okay. Okay, good. Then, just to be sure, once we do this, we need to make sure that we are in the ROS workspace folder, and then we need to source this file, basically sourcing a file. here it doesn't say source. It's basically just running a script. Source is for running bash scripts. And we run this file, which is called setup.bash, sorry. And this is basically just defining environment variables in our code. So we do this. And then we also source our bash RC. This is a file that runs every time you open a terminal. It runs a file. Maybe I can let you see it. So this is the file that runs every time you open a terminal, and it has a certain number of instructions, and it defines environment variables and such things. So then we need to source it here just to update the changes that we've made, and that's it. Then, because one of the visualization tools that we're going to use is not installed by default in the virtual machine, we're going to need to install it now. So to do, we first need to update our list of repositories. So we do sudo apt. Apt is just basically the application that is used to install software in Ubuntu. So you do sudo apt update, and then it's going to ask you for the sudo. It's just to run as a, it's basically the equivalent of running as an admin in Windows. Then you type your password, and then it will start updating your repositories. Okay. Okay, good. Then we need to run sudo apt install ROS Kinematic, which is our distro, joint. Let's see if I completes. Yes, joint state. So sometimes when you have multiple options, if you use tab, it will show you all of the alternatives that you have. Publisher, GUI, and then we hit this. I have already installed it, so it's not doing much. So you should be able to install it as long as you have internet. Okay, good. So now we have all of what we need to start. Okay. Okay, so let's go to the part one of this lab session, which is learning how to use a URDF description files. By the way, if you get stuck in something or you get an error, please let me know. If it's easy to solve, we can try to debug it now. If not, we can please write it down, and we can try to debug it after the lecture. And we can exchange some emails. But I tried this lab session in 2 different computers, and also Professor Foki tried it. Of course, all systems are different, so it can always go wrong. So don't hesitate to ask. So let's start by inspecting a simple geometry file. So what we want to do is we want to move to the folder where this basic geometry file is. So we're going to do cd. If you have an Italian keyboard, writing a tilde, it's going to be difficult for you. So you can do the tilde. It's basically your home folder, this symbol. So you do instead cd home student, and then this is the equivalent of the tilde. And then you do ROS workspace source locosim visualize UR, and then UR4 description. So this is the place where we are storing our description files, which are URDF files. Okay. So if you want to see the contents of a folder, you just type LL, and then you will see the contents of the folder. Okay. So let's start by inspecting the file simple geometry URDF. So gedit, it's basically the notepad of Ubuntu. So we type gedit simple geometry.urdf. Okay. And then it will open this window, which I'll make it larger. Let's see if I can visualize it a bit. Let's make it a bit bigger. Okay. No, this is the type. Editor spaces, your fonts and colors. Okay. So let's try to make it a bit larger. Okay. Is this large enough? So this is a .urdf file. However, the extension is not that important because we're using XML. So this is what it's telling Ross that this is an XML file. This header, which is defining just XML and the version. I've never seen a different number than 1.0 here. So this is just telling Ross that this is an XML file. And first, we say that this is an XML file that is going well, it's a URDF file that is going to define a robot. In this case, I'm going to just call it simple geometry, and it's going to use a SACRO convention, which stands for XML macros. And it's just a scripting language that it's very similar to HTML, but it's the main purpose of XML is to store data and parameters, whereas, for example, HTML is to display visual information. So first, let's just go and inspect it because we want to get to the kinematics and dynamics part. So the first part that we see here, it's the it's what we call the world link. And here I'm opening and closing this this tag with this of what if you compare it with the one below, this one has an opening tag on top and an opening tag in the bottom. So if the world doesn't have any parameter, so we just open and close it in the same line. Then what's in between here, this is the second, this is a joint, this is defining a joint, and the name of the joint is world joint, and it's of type fixed, and it's just basically connecting what the link that we just defined, which is the world, and the base link, which is the link that is going to be after us, which is a child of the joint. And it has a defined origin with respect to the to the parent link, and an XYZ position with respect to the parent link. So then we define the base link. So for example, you can use so this is a very basic example, and you can use a basic geometry to define a link. So in this case, we're using a box, and this box has a certain size. So you put 3 dimensions, and this is a visual property. Then you can have a collision property. In general, you want the collision property to match. Although for some applications, you might want to have a different collision. So let's say a larger collision property. For example, if you don't trust your mesh, because you can also use a mesh from STL, you can use a different size of the geometry. And then we have a joint, which we're going to call shoulder pan joint, because this is the name that we're going to use for our manipulator. And this is of type revolute. You need to define the type. The parent of the joint, it's the base link. Then it has a child, which is the shoulder link, which is defined afterwards. The origin of the joint is this one, and then it has an XYZ displacement from the previous link. So from the previous link frame. And here It's defining the axis of rotation of the joint, and in this case, it's the z-axis. And then here you can define torque limits and joint limits. Here, for example, there are not joint limits. It's going from pi to minus pi, which is basically the entire range of motion of the joint, and it has a limit on velocity. Okay, and then there's the shoulder link. In this case, we use a cylinder, and then you need to define the radius and the length of the cylinder. And for example, here I'm also defining inertial properties of the cylinder. However, in this first example, we're not going to use any inertial properties because it's just visualization. But when we start looking into dynamics, then these properties are going to become handy. So this is the URDF of our simple geometry. So let's try to So a second step that we can do is so let's close this. So to kill a process in a terminal, you do Control-C. So this is like a sort of a source of confusion because Control-C in the terminal in Ubuntu kills a process. So it's not used for copy-paste. For copy, you use Control-Shift-C. Then we go to the so we're gonna look at a different file now, which is UR4 to rlinks.urdf. And this is basically also it only has 2 links, but now I'm gonna open it. And the first link and joint are the same because they're the fixed word frame, but now the base link is not described anymore by a simple box, but rather we are getting a mesh. Let me try to remove this. Okay, here it is. So it is getting a mesh file, a mesh contained from an STL file. So this STL file, it's the output of many CAD softwares such as SolidWorks, and you can use it to basically define the geometry and also the collision values of your link. Then here we specify the inertial values of the so we make the collision and the geometry be the same, and then we specify the inertial values of this joint. Now we see here that we have something called inertia, and this is basically the inertia tensor of the link, and it's basically just giving us the values of the diagonal, and this is because it's taking the moment the inertia tensor located at the center of mass. So if the center of inertia expressed with respect to the center of mass, so if it is expressed with respect to the center of mass, you only get the diagonal terms of the tensor of inertia. And this is what this means. Then for the joint, we basically have the same parameters as before, and we also define a mesh for the shoulder link. And now an interesting thing about this, although today we're not going to use it, is that this transmission name, it's something that is used in some physics simulators. Today we're going to simulate our own physics with the dynamics model, but for example, Gazebo, which is the most widely used software for simulation in ROS, uses a physics engine called ODE, and it requires the type of transmission that you do between joints. So for example, here you can specify if you have a gearbox, if you're sending torques or positions to your actuator. So this is basically defining your actuator interface. Okay, so now that we saw the basic and the 2 links, how am I doing with time? Now we want to visualize this, right, in Arvis. So let's switch to the folder in which we have what we call our launch files. So home, student, ROS workspace, source, locusim, and now we go to our visualize UR, and inside visualize UR we go to launch. Okay, and inside we have a file called visualize_UR4.launch, and let's inspect it. Okay, I had already opened gedit. So of course we inspected as the other ones. We do gedit visualize UR4.launch, and basically a launch file, what it does is that it allows you to launch multiple nodes at the same time. And so, for example, you can run a node by just typing ROS run. And then, of course, I have too many possibilities. Let's see if I can have this. So this is a node. Now, I think I can launch Arvis. So Arvis, there's a launch for a node for Arvis. And then you can launch it by just typing this in the terminal. Although, if you launch it, then it will basically, I haven't launched the ROS core, so let me try something. The ROS master. Well, let's see if it works. So the ROS master blocks out the terminal. So let me open another terminal, and then I do ROS run, Arvis. So this is just going to open the visualizer, right? So this is our visualizer. And then if I wanted to open another node, then I would have to open another terminal, or put the ampersand command here in the ampersand character here, and putting an ampersand allows you to run multiple commands. But I mean, this is not efficient, so that's why launch files were created. So you can basically just make a script and put all the nodes that you want to launch with the parameters that you want to launch, and then and then just run a single file to launch it. So here again, it's an XML file. As I mentioned, the extension doesn't matter when you're writing an XML file. What matters is putting this top line, and then you need to specify that this is a launch file. So ROS knows that this is a launch file. So you do it with this tag. Remember that you need to open and close the tag, and then we specify a number of arguments. So here, for example, these are custom arguments. This is where I can add a custom argument here, which I want. And then what I'm doing here is that I'm specifying the configuration file of Arvis. In Arvis, your window. So let me see if I can open it again. I'll open another terminal here. Okay. In Arvis, let's launch this again. ROS run Arvis. So this window, if you like these settings, you can just save it as a config file, as a configuration file, and then it will you can use it to keep it that configuration file, and then this becomes important when you're for example using different camera views and looking at different models. It's important to have like a good config file. So here, for example, we're defining this argument so that you can set any file as config file, and then we have a default value, which is the config file that we're using. Then we have an argument called test joints, which will allow us to launch a user interface to just visualize and move the joints. And then the name of the robot. In our case, the default value is basically the one that we're going to be using in the entire lab session. And robot name will contain a URDF, the name of a URDF file. Here, this omit topics is just don't take care of it. This is not standard. This is, I just made it to avoid certain problems while running this this launch file. And then here in parent name robot description, this is just specifying the location of where our robot description file is. So here is just finding where the Sacro Python library is, so that here you're just telling where it can find the how to interpret Sacro files, and telling Rose how to interpret Sacro files. And then here we have defined this environment variable in our .bashrc. Remember that I opened our .bashrc. So this environment variable is defined there, and it's also in this. Then we point to the folder where our robot descriptions files are, and then we plug in the argument that it's our robot name here. So for example, here we could put our URDF file, which is a simple geometry, or we can put our UR4 and such and so on and so forth. Then here we're just launching the node to test the joins, and this launches this is basically doing the same thing that I was doing in the terminal, which is running the Arvis node. So here you specify the name of the node, Arvis, the package, which remember that type ROS run Arvis, that's the name of the package. Then the name of the executable that you're running, it's Arvis. And then the robot state publisher, it's publishing the values of the joins. Okay, so now that we inspected this, let's see what it does. So let's go to our terminal. Let's go here, where I have it. Let me make it larger. So to launch of a ROS launch file, then you do ROS launch, and then you do. I know the name of where our launch file is. So basically, we want to launch this visualize for .launch file, and let's run it with the argument of the simple geometry. So this is the name of our file, and let's launch it. Okay, so this opens our simple geometry. Remember that we had a box and a cylinder. Now, let me make it a bit smaller so we can see. So here we have it. And then remember that we only define one joint. So here we can play around with our joint. Right? And then, yeah, just to verify that it's working. Okay, let's move on. So now let's try to launch the second one that we did, which was the one with two links, but with the meshes. So let's see how it looks. So for example, here, it had basically the same parameters for the location of the frames, but now we have, we have the meshes of our base link and our shoulder link. And if we move our interface, we see that we can move it the same as the previous one. Okay. Okay, good. Let's continue. Simple geometry. Okay, so something that is important is that I made this argument as default true. If you put false, then it won't do anything because the values of the joints are not being published. So you're just gonna see a white thing there, you see? And that's basically just the meshes, but there's no information about where the joints are. So that's why, I mean, it launches, but it doesn't know what to do with it because there's no information about the joint positions. Okay, so now let's visualize our the manipulator that we're going to be using in this lab. So the default argument of our launch file was, so I'm just going to write it down. It's UR4 robot, and then this is going to launch our URDF file. Okay, So here we already have our 4 joints. Of course, you know that it's a 4 degree of freedom manipulator. Here we have our shoulder pan joint, our shoulder lift joint, our elbow joint, and our wrist joint. Okay. So for example, this type of manipulator, I modified it for from a 6 degree of freedom one, just to have an easier way to compute the inverse and direct kinematics, the inverse and direct and the forward and inverse dynamics. But this could also be a manipulator with a bentos at the end. So for example, you suck air, you have a pneumatic actuator at the end, and you can suck air. For example, the newest robot from Boston Dynamics, of course, has an array of this kind of actuators to grab boxes. Okay, so we visualize our robot. Now, this is not the right terminal. So let's kill the process. Now, I want to show you something just to connect it with what I was mentioning at the beginning about the topics. So what, let's relaunch this again. And I don't know if I will have enough screen, but let's see. Okay, let's do something like this. Okay. Okay, let's put our, tell me.
How can I show the grid?
The grid, yes. So to show the grid, you need, oh, I'm running, oh, sorry, I'm in my local PC because I'm running it in 2 places. So to show the grid, there's on the right, I don't see if you see this arrow here. You click on it and it shows you basically the elements that are loaded into Arvis. So one of those elements is the grid. So to remove, but I think that by default, the grid that you have, the size of the grid that you have is super small. So you're seeing a gray, yes. So change the cell size to 0.1. And then you should be able to see a similar size. Good. And then you can change also the number of cells. So for example, if I do 10 here, you see here this. If I do 1,000, you see this. So that's it.
And also remove the names of the joints.
Yes, you can also remove the names by, I think you have a TR, a TF. Where are the names? I think you're visualizing TF. Yes, you're visualizing TF. So TF, it's basically showing the transformation between each of the joints.
Okay.
If you click on it, then you remove it. And of course, I'm showing the axis of each of the links here, so that you can. So to look at them, you have your robot model, and then you have. So you're probably looking at it like this. So to see the links, you click on this small arrow here, and then you will see all the links. Probably these are also collapsed. So you just need to click on the arrows, and then to see the axis, you click on the axis, basically. Oh, let's make it a bit, maybe I can make this a bit smaller so that we can see. So for example, if we want to remove oh, I'm removing the entire link. The axis, we click on this, and then we can see it go and say, okay. Okay, now let me do this. Okay, so I'm gonna open another terminal. You've seen me playing with Terminator, but I haven't told you how to. We use Terminator because it's practical, because you can just split your terminal in multiple terminals. So for example, if you do Control-Shift-O, it didn't work, Control-Shift-O. That's happening. Yeah, here. If you do Control-Shift-O, then it will split your terminal in 2 vertically. If you do Control-Shift-E, it will split it vertically. The previous one was horizontally. Now to close a terminal, you can do Control-Shift-W, or you can also right-click on it and close. So what I wanted to show you, this is already running in a separate terminal. It's what the what our GUI is actually doing. So let's type. I'm already in 1.4 of our instruction set. So we want to visualize actually what our GUI is doing. So to do this, we type rows topic echo, and then we do join states. Okay, so what's basically doing, we're echoing the topic join states. So what this means is that we're gonna just see what is being published onto this, well, what's being in this topic, what's being sent to this topic. Okay, so for example, in our case, we see that you're gonna see that this is printing a lot of values in time. So it's giving us the time at which the timestamp of at which these values were sent to the or published to the topic, and then it's going to show us a number of fields. So for example, what our joint state publisher is doing, or what our gather interface is doing, I'm going to move the shoulder pan joint, and you'll see the value of the shoulder pan joint changing there. Okay, so this is accessible to every node in our ROS ecosystem. So one nice thing about having this standard is that you can basically develop any type, you can develop a controller and publish onto this topic. And this is what we're going to be doing today, to just simulate the dynamics, to change the motion of the joints. Okay. So let's move to kinematics. So let's do something that is very important, which is whenever we're working with PyCharm in our virtual machine, and we want to develop in ROS, we need to run PyCharm from our terminal, because this loads the bash RC that we have. Otherwise, we would have to run special commands in PyCharm, and it's more difficult. So if you run PyCharm from the terminal, let me close mine so that I can do it from scratch. Okay, so let me close this terminal. Let me clean this a bit. If you type reset on a terminal, it cleans it. So let's type PyCharm-community. Okay. And this launches PyCharm. So in my case, it opened in the project that I had already opened. Of course, for you, it might indicate a different thing. So what we're going to do is, let's just from scratch, we do open, and then we go to the folder. So there's this tree structure. So you go to home, student, then ROS workspace, and then locusyn, and then I'm going to cancel it because I have already opened. Well, let's open it in this window. So this opens the same thing. Okay, I had already opened files and run things. So we're just opening our project. So okay, let's take a look at what we have on our left. So what we see is this is the locusyn folder. Let me collapse everything. And what we're going to be mainly working with is this L3_kinematics dynamics, which is lab tree on kinematics and dynamics. Okay. And there we have three main files, which are L3 kinematics, which is going to run the kinematics part of our lab session today. L3 dynamics, which is going to run the dynamics, and then a configuration file. Let's inspect a bit the configuration file just so that you know what it's doing. It's just defining the duration of our simulations as we go. This is just a sign. So, for example, I don't know if you recall that in our MATLAB lab, we defined in our simulation, we had to define the step time at which we were discretizing the simulation. So we're basically defining this here, and we're performing the integration ourselves. What we will do this via an Euler forward path, a forward Euler integration. Sorry. And then we have a slowdown factor. So in this case, the slowdown factor, it's going to be 10. And then we define the name of the end effector link as it is in our URDF file. Let's see if we can see it here. So this is the URDF that we're going to be using today. Of course, it's much more complex because it's a full robot, but it's made under the same principles as the other two. So we have the base link here, the shoulder pan joint, the shoulder link, shoulder lift joint, and so on and so forth. And let's look for the one that we care, which is our end effector link. So this name coincides with the one that we have here. Okay. And then here we're defining the initial conditions of the position, velocity, and acceleration. Although for the kinematics part, we only cared about position for now. Well, and velocity, sorry. Acceleration, we care about position and velocity. So okay. Let's go on. So let's inspect our main file on the kinematics. So the main file of the kinematics, it's in our L3 underscore kinematics dynamics. And then you go to L3 underscore kinematics. And then you'll see the file. So as we know, at the beginning of a Python file, we have to import the libraries that we're going to be using. And in our case, the most important ones are, so these are two files that contain functionalities that we're going to be using. So for example, what we're going to be using to publish to the joint state topic, it's going to be this function imported from the ROS publish UR4. And this is basically just publishing the joint values. Then we are going to be working on developing these functions that are going to help us to compute the direct kinematics, the geometric Jacobian, which is called compute end effector Jacobian, the numerical inverse kinematic, the numerical inverse kinematics, a polynomial trajectory, a way to find a polynomial trajectory based on a fifth order polynomial, a conversion from the geometric to the analytic Jacobian, and a transformation from rod to Euler angles, from rotation matrix to Euler angles. So let's see the first part of our lab so the first step to start working on the kinematics, which is let me take out the description now that we've been through the settings and the files. So let's go through the description, right? So we're already at this point, and this is what I just mentioned about the main three files that we're going to be using. And now let's start with the direct kinematics part. So the first step that we're gonna need, because actually everything of what we're going to be doing depends on the previous step. So because, for example, to compute the geometric Jacobian, you need to know the direct kinematics. To compute the numerical inverse kinematics, you need the analytical Jacobian, which comes from the conversion from the geometric to the analytical Jacobian, and so on and so forth. So the first step that we're going to do is to find the homogeneous transformation matrix from the Wolfram to the end effector. And as we saw in the lectures, specifically in lecture E1, we need to do the composition of matrices from the world from the world to the to joint one, to link one, then to link two, then to link three, and then we continue going through the homogeneous transformation matrix until we get the final the composite homogeneous transformation matrix. So let's modify this function. So let's go to my virtual machine, and this function is located inside of the folder base controller, utils, and then we go to kin-din utils. Okay. So let's inspect this file. So at the beginning, I'm just setting the robot parameters that I got from the URDF. So I am doing this because we're going to be comparing what we're doing with the functions that come out of Pinocchio, which has these facilities already implemented. This is just to get a better understanding of what's going in behind the functionalities of Pinocchio. And Pinocchio reads these values directly from the URDF. I am here just hard coding them because this is very specific for our example. So I'm defining the links of the lengths. You see that there are more than 4 lengths. That's because maybe I can show you if this is still open. If you see here, there is the links are not well aligned. So for example, for this joint, so the length 1 is just from the base to the first frame, and which is the 0.08, this 8 centimeters. Then the second one, it's just again just a displacement along this axis, but the third one is a displacement along the z-axis, and then a negative displacement along the y-axis. So just I know that which axis are this because this is RGB. So R is X, G is so red, green, and blue. Red is X, green is Y, and Z is blue. So here it's a negative displacement along the y-axis. So that's why I have 2 lengths here. And this is why you see more than those. But you can find all of this data. You can inspect the URDF, and then you can find this here. Then I'm just defining the inertia tensors, again, from the URDF. From the values, as I mentioned, we have here the diagonal matrices of the inertia tensors and the masses. And then this function that is called set robot parameters, it's basically outputting a vector with the lengths of the links, the inertia tensors, and an array, because these are NumPy arrays. With this, then I added a functionality just to do the transformation from rotation to Euler angles. It's just to make it, because we're going to need it later on, and it's not very interesting to derive it. So let's start with the computation of the direct kinematics. Okay. So we have our first link. So what we want to do first, okay, I'm missing the function itself. Why is it? This is just a syntax error, I think. Yes. So PyCharm puts squiggly lines if you have also syntax errors. So it's just complaining that it doesn't like my grammar. So let's define the first transformation from the world frame to joint 1. So let's use our model that we already have open. If you already closed it, you can relaunch it by typing in the terminal. So a general way to do it, and will not fail, is do this. Then goes workspace, other C, locus in, visualize, launch, and then this launches this. What you're seeing here is what launches the file. Okay, Tell me.
Sorry, but I don't have the file. I don't know why, but in the folder.
Were you able to run it before? Or since we started, you haven't been able to run it?
I don't have a Kinematic, the file you open now.
So you mean in the PyCharm,
Yes.
Kindin utils.
Yes, and I have other files. Like
Probably you're in a different folder.
I'm that folder.
In L3 underscore kinematics and dynamics.
No, okay.
Yeah, because this is wrong from my part now, because I wanted to make it self-contained, so I copied some functions from the folder in which you were.
Okay, I was in the robot control.
Yes. Yeah. Good that we sorted that out. So let's see our transform. So this is from the base link or the world frame to link 1. So we see that there's just a displacement along the z-axis, which is this blue axis, and then we also see that there is a rotation for this joint, right? So we see that along the z-axis as well. So what we want to do, it's I'm at homogeneous transformation matrix, which contains a rotation about the z-axis and a translation about the z-axis, but this translation, the rotation depends on the value of the shoulder pan joint. So I'm going to cheat a bit because I already have this. Where is this? Yes, here it is. Hopefully this works. Okay, good. This worked. So just to explain what I've just said, the rotation part of the homogeneous transformation matrix, it's just a rotation about the z-axis of the value of joint of the first joint. Remember that Python it's 0 indexed, so that's why it's 0, but it's actually it's joint 1. So we have a rotation, and then this is L1, which is the displacement of our homogeneous transformation matrix. Okay. Now let's do the second one, which is our transformation from 1 to 2. Then I'm just going to copy this. Okay, here it is. So now we see that we have a rotation. So we have two things, a translation and a rotation. The translation is rigid along the y-axis, and we also have a rotation about so it's important to start always from 0 so that you can see what is the orientation of the joint when it's at 0 angle, so that you can see if it has an initial rotation. So in our case, we have a rotation about the y-axis, and this is so the y-axis is the green axis here, and which places our z-axis to go along the direction, the longitudinal direction of the joint of the arm, and this is a positive rotation about the y-axis. Okay, and then after that we have the rotation of the joint itself, again about the y-axis. Okay, now this might come as a confusion for some of you, because in our lectures we define always the Z axis to be the axis of motion of the joint. However, in ARVIS or in the URDF, this is defined as a property of the URDF. So you can mess around with the URDF and make the axis fixed, but sometimes it's better to just get the understanding of which is the axis of rotation, and then once you're computing, for example, the geometric Jacobian, you know that the axis of rotations that you need, it's the Z axis. So for example, in this case, instead of doing a rotation about the Y axis, we would do a rotation about the X axis, a negative rotation about the X axis, so that the axis of rotation of our joint, it's pointing in the direction of in the same direction as the green one in the second joint. Okay, so let's do this. So again, I'm gonna cheat. So I'm gonna copy this. And then here I have, so you see that I copied 2. It's because I'm making the transformation in 2 parts. So this matrix is just a rotation about the Y-axis. So this is basically sine of 90 degrees. So it's a 90 degrees rotation. Let me show you here. So this is a 90 degrees rotation about the Y-axis. Okay, and the displacement again along the Y-axis. So this is the L2 that you see here, and this is the 90 degrees rotation about the Y-axis. And then we have the transformation related to the rotation of the angle. Now I'm running out of space, but let's see. Okay, so this is again a rotation about the Y-axis. But now of Q radians of Q1, well, this is Q2 actually, radians, which is the value of the joint that we have there. And yes, this is and there's no translational part because we already took care of it in our rigid transform. Okay, so I think that the rest of the procedure is kind of the same. You need to understand that there's the rigid transform, so from here to here. So you have a translation between these 2 vectors, and then you have the rotation of the vector, and then you go until you get to the end effector. Okay. So I'm going to complete my joints, and I'm going to copy them here. Okay, good. So we have T01, T12, T23, T34, and T4 to the end effector. I'm not gonna work out all of this because there's not enough time and there are more interesting things to do. I'm gonna push the code to the same branch that you're using now for the lab with the solutions so that you can check this. And now what we want to do is compute so this is what we're calling the global homogeneous transformation matrices. No, sorry, the local. So these are the local homogeneous transformation matrices, which are basically from one link to the other. What we want is the global homogeneous transformation matrices. So let's comment here. Okay, so to do that, we need to do the matrix multiplication. So T01, we already have. Now T02 would be MP dot. Remember that in NumPy, the multiplication is not the star, but it's rather it's MP dot. Let me just check something. Yes, this is fine. Actually, another way to do it with one single argument is T 01 dot T 1 T underscore 1 2, which we already computed. And then we can do T03, which is equal to T02 dot T23. And then this is just typing this multiple times. I'm just going to copy this here. Ah, yes, I was skipping the rigid transforms. So remember that we had to multiply for by the rigid transforms. So here are the full direct kinematics, and I'm gonna output all of them of this from this function because they are useful. They're going to be useful also for the dynamics part because you need to compute, well, also for the geometric Jacobian actually, because you need to compute the location of the link frames with respect to the world, and you can get them from the homogeneous transformation matrices. Okay, so this is the first exercise of the direct kinematics. So would you guys like to have a break now, or do you want to finish the part of kinematics? Break? Okay. Let's have a 5-minute break just to be able to continue fast, and we'll reconvene as soon as the 5 minutes passes. So we'll see each other at 6:02.
Excuse me, is it possible for you to show us like the matrices that you copied? So maybe we
Yes.
can.
Yes, of course.
Thank you.
You want from 0?
It's okay for me, at least from.
Okay, let's put it from here. Maybe I can make it a bit. I'll try to make it more legible. So it's a trade-off between making it able to read and let me see. Well, let's keep it like this, and then tell me if you want to reach the final one.
Okay, thank you.
Sorry, everyone. We're having a bit of trouble because I tried to close the window blinds and and then I turned off the projector. But I'll try again. Just 1 second. Let's see if I manage to get it done. Okay. Seems like it's working. Okay, great. Okay, we're back. Can everybody hear me?
Yes.
Okay, great. Okay. So we would like to verify our computation. So a good way to do it is by using our Pinocchio library. And let's open the file L3_kinematics. And let's go all the way to the top of the file. Wait, okay, here. Well, first of all, we have our direct kinematics function called from here, and then we're just calling it dk. So let's call it here direct kinematics, and then we just pull it as dk. And then we have a configuration. All of these functions exist, although they are currently empty. So you'll get an error if you try to run this. Then I'll try to explain more or less how it moves, how it goes. Then we have our ROS publisher defined. This is just instantiating an object for our publisher that we can later use its values and its methods. And then we are also instantiating our robot, which is defined by this function getRobotModel. Number of initializations for logging. Also the initialization of the joint variables. Here we're having a QDesired. Here it's just I just kept them because we had some logging features for control, but in this case we don't have necessarily a desired position, velocity, and acceleration. In this case, we're initializing them with the values of Q0 in our config file L3_conf.py. Okay, here we're defining the frame, the value that we define in our config file. It's here, which is the frame E. And then here we reach finally the point where we compute our direct kinematics function. This is line 55 of L3_kinematics. And here you see that the output of the direct kinematics functions are all of the homogeneous transformation matrices. And now we're going to compare the output of this with what's coming out of Pinocchio. Okay, so as I said, if we try to run this, this is going to give us an error. So let's put a breakpoint here. At least we know that everything on top is able to run. So to put a breakpoint, you just need to click on the right of the number. And to debug, there's a question in the chat, which is how can I set the transparency on Arvis? Okay, let me show you. Maybe this is related to the question of your colleague. Before, this is Arvis open, right? So before, you were probably looking at something like this, not like this, but then, yeah, something like this, right? This is just the plane. Now I put too many. Hopefully, I hope my computer doesn't die. Okay. So this is because the cell size is too small. So you can reduce the size of the cell, increase the size of the cell by changing this value here in the grid. And this will give you a larger size of grid, and then you don't have it transparent. And also a useful thing to visualize the frame is change the transparency of the robot. So to change that is you need to change this parameter alpha here. So for example, probably you have 1 now, and this is how it looks with the full transparency. You can change it by putting here 0.5, and this is what you get. And this is what gives you the inside of the robot. Okay, good. Let's go back to PyCharm. Okay, good. Now, for now, we need to kill our process that is currently running because they're calling the same file and they're both setting joint states. So there's going to be a conflict between the two nodes that are running. So maybe we can just leave it and then we'll see what happens. And this is because there's conflicting signals of the nodes. So so let's say they're publishing at the same frequency. So it publishes one value, the Arvis takes this value, and then this publishes another one, which is in a completely different location. So you're gonna see the robot kind of flickering. Or maybe not. Let's see. Okay, so okay, so we put a breakpoint here by clicking next to the number, which is 64. So this is not going to run this instruction. And then we're gonna run debug. Because this is loading another file. I'm gonna try to run this. This is going to give me an error. Yes, I understand. Okay, so when you run it, actually by default, it closes everything, every node that it's open. So that's fine. So now to run this file, to debug this file, you need to set it here and then edit the configurations to run this file. An easy way to run it is just typing Ctrl+Shift+F10, and it will run this file. And then it would set it by default here. Of course, now it's gonna throw errors because we haven't completed the functions. But now let's try to debug this one. It's opening, and it's opening here. Okay. And then here we have the name of our variables. An easy thing that we could have done was to print this, and we could have seen it in the printouts. But let's use the debug feature of PyCharm, because in the future, if you have lots of variables, it's really hard to get a hold of it. So here we see. So let's go through the code actually. So here we're computing our direct kinematics functions, the homogeneous transformation matrix. Then we need to run this. So this is related to Pinocchio because this sets all of the constants and variables that are related to our robot. So this loads the parameters, does everything, and then it computes all of the terms of the dynamics and kinematics functions. If you don't run this is going to throw zeros. Then we have this function x. This is not a function. This variable x, and then this is defined as by this function, which is called frame placement, and then we define the values of our joints, which are q, which at this moment are the ones that we gave on the q0 on the configuration file, and the name of the joint that we want to find, right? And then this gives us the translation part of our homogeneous transformation matrix, and O gives us the rotation part. So this is going to give us the rotational matrix of the homogeneous transformation matrix. Now, here, actually, I was looking for the name of the variable here, but actually, when you debug, it shows you the value of the variable right next to it. So the difference between X and our homogeneous transformation vector, which is the rightmost tree vector of our homogeneous transformation matrix. So the top right vector of the homogeneous transformation matrix. So this difference, it's equal to 0, which means that our direct kinematics work. And also the rotation matrix, it's also full of zeros. I don't want to open it in another window, but it is full of zeros. I mean, you can see that first. Oh, it's actually all of this. These are the 3 rows of the homogeneous rotational part of the homogeneous transformation matrix. So this means that our direct kinematics function works. Now let's move on to the next part of our lab session. Let me take out our geometry, our description. Now the next part is to compute the geometric Jacobian. And now that we remember that the geometric Jacobian only depends on the direct kinematics. And it's given by these expressions. So the geometric Jacobian, it's given by the linear part of the linear contribution of each of the joints on top, and the angular contribution to the velocity of each of the joints, where these linear and angular contributions are given by this too. So if I is prismatic, it's just the zi vector. Remember the axis of motion of the joint, and if it's revolute, it's the cross product of the different of the zi vector cross the difference of the end effector vector. So the connecting vector between the joint, the link frame, and the end effector frame, expressed with respect to the world. In our case, all of our joints are revolute, and let's jump into the code. Okay, good. So let me get to the function, and here it is. So what do we need for our computation of the Jacobian matrix? So if we look back at this, we need to compute this for each of the joints. So we need to compute vector z, and we also need the positions of each of the link frames. Okay, so to achieve this, let's start with the easy part, which is the position of the link frames. Okay, now let me remember. So we need the position of link 0 with respect to the world, the position of link 1 with respect to the world, link 2 with respect to the world, link 4. So let's do this real quick. 2, 3, 4, E. Now to get the positions of this, we can take advantage of the fact that we already have our inverse kinematics function, direct kinematics function. So what I will do is this. So I'm just copying the values of the direct kinematics, and then let me just copy the name just so that I don't make any mistake here. And this will provide us the homogeneous transformation matrix. So for vector 0, 1, the vector of position is this. Not 9, 1, 0, 1. And then we get the homogeneous transformation, the vector of position of link 1. and so on and so forth. So I'm going to cheat again because I already have this. Let's get it like this. Okay. Okay, now let's go to the part that is a bit more difficult. And to do this, we're going to aid ourselves with our drawing. So remember that we want the z-axis to be the axis of rotation of the joint. So joint 1 is its axis of rotation. It's this blue axis, which is basically the z-axis, and it's pointing in the same direction as the base link. So this is very simple. Usually the first link is very simple in whenever you are working out the geometric Jacobian. So this first link, this set I, it's just basically 0, 0, 1. Okay, now we want to get the z-axis that transforms. So here, instead of having this y-axis being the axis of rotation of the link, what we want to have is that we're going to do the transformation such that our axis of rotation is the z-axis. So what we need to do, as I mentioned before, when I was working out the direct kinematics, in this case, what we're going to do is that we're going to do a rotation about the x-axis of 90 degrees, and this is going to be a negative rotation about the x-axis. So we rotate in this direction, and this way we see that this blue line is going to be aligned with this green line, and then the translation is going to be basically the same. So I already did this computation, so let me get it here. Okay. Yes. So this is the rotation of 90 degrees about the x-axis. I need to go back to the virtual machine. So I'm going to do this computation before because we need it here. And then what we want is basically the transformation from the link frame 1 to link frame 2, taking into account that we want the z-axis to be the axis of rotation. So we pre-multiply our rotation matrix by the rotation matrix that we already had. So basically what I'm doing here, it's just getting the rotation matrix from 0 to 1 and then getting the rotation to the to the set frame. Remember that when we talk about the z-axis, we only care about them being oriented in the same direction. So we don't care about the translations. And this was the trick that we did just to visualize. So we usually translate the frame to the same point as the previous joint, and then we can perform the rotations on top of them. So for example, if we look at Arves, instead of thinking about, oh, this is going to rotate and this is going to move at a certain distance from this one. So I'm talking about frame 1 to 2. So you put frame 2 aligned with frame 1, and then you perform the rotations. So the first rotation, it's a negative. It's a negative rotation. It's the rotation so the transformation that the first link is doing, and then we do the 90 degrees rotation. So this is basically what I'm doing here. Hopefully we went through that. Then we need to apply this transformation to the 0, 0, 1 vector, which is the set. So if this was expressed in the same frame, we basically, for set 2, we need to apply, this is the same vector as set 1. So we apply this transformation matrix that we do R set 2 dot set 1, which is not defined yet. Actually, I can do already this. Okay, and this gives us a rotation. So the position of the vector set 2. Now, let's go back to our drawing, and what we can notice is that actually the axis of rotation of let's pull out our what am I doing? Okay. Joint state publisher here. Is that the axis of rotation is actually pointing in the same direction for all of the 3 joints, right? So this one is this one. The elbow joint is this one. And this is this one. So all of these axes are pointing always in the same direction. If you translate those frames to the frame of 2, to the origin of frame 2, these are going to be always aligned. So actually, the rest of the set vectors are just the same as set 2. And just to verify if I'm not making any mistake, this is what we have here. Okay, good. Then let's put out our equation again. So we already have all of the information that we need. So let's get our cross products first. So how did I do this in an efficient way? Yeah, so first I computed the difference in the from the end effector to the link frames, which is this one. So basically I'm subtracting the position of the end effector with respect to the world minus the position of the link frame with respect to the world. And we do this for all the joints, and we're going to be needing this to do the cross product. So then we perform the cross product. Now, how did I do this? I think I stacked. So yes, I computed the linear and angular contribution separately. So this is the linear contribution. This JP is the linear contribution. So it's basically for all of the joints, we have the cross product of vector zi cross the with the vector from the link frame to the end effector frame, and we repeat this for all of the elements in the for all of the links in the kinematic chain. And then the rotational part, if we look back at our equation, then we have just the set axis. Okay. Then we need to stack this. So to stack this, we need to use the. I'm just gonna copy already this. And oh, this is already here. Okay. Okay. So we need to stack JP and JO. So to do this, we use the numpy function vstack, and I need to transpose them because the array is the structure of the array. It's a transpose one. When you construct this, I'm just I would have had to put like square brackets on each of them if I wanted to write, but I'm just transposing them. And then the output of this function is not only going to be the geometric Jacobian, but it's also going to be the set axis, because we're going to need this for the dynamics function to compute the recursive Newton-Euler. Okay. So we can verify this again using Pinocchio. And now that we have this, I think I'm still debugging. So I'm gonna stop debugging, please. Okay. And now I'm gonna put my breakpoint here in the analytic Jacobian. This is a computation of the analytic Jacobian. Okay. So let's remove this breakpoint and let's run the debugger. Let's go back. Ooh, there's an error here. Oh, of course, I didn't do a multiplication here. Stop. Rerun. Okay. And now we see that the difference between our Jacobians is the same. All values are zeros. Okay, that's great.
Yeah, sorry, Octavio, the
Tell me.
J6, the name of the variable is misleading. Of course, is a typo. The Jacobian is only 4 columns because you have 4 joints.
Yeah, but this is J6 because it takes the 3 variables of velocity and the 3 variables of orientation. It's called J6. It's not a typo, but it's in another file on control. You're only taking the first 3 rows of the Jacobian. That's why it's called J6. It was just that.
Okay.
I think that in that file, you just wanted the position to do position control and not the orientation.
Okay. Yeah, it's just I don't like it much. Maybe we can change it.
We can remove it, of course. But then I need to put different names on the variables.
Yeah, no worries.
Okay. Okay, good. So now we found that our geometric Jacobian is the same. So let's compute our analytical Jacobian. So remember that our analytical Jacobian, we can compute it based on intuition, inspection of our robot, or we can just perform a transformation between the geometric with the geometric Jacobian. And this transformation of the geometric Jacobian is based on the relation between the angular velocity and the Euler angle rate, which is this matrix here. Okay. Yes. Okay. So what we are going to do is to compute the function that does this transformation. Let's stop the debugger just to have a cleaner view. And let's go back to Kinding utils. And this is the computation of the analytical Jacobian. So, okay, first we need to define our transformation matrix. So again, let's go the easy way. So I'm gonna copy this top part. Yes. Yes, I just need to remind. Yes, because the arguments of this function, it's both the geometric Jacobian and the homogeneous transformation matrix to the end effector. So because we need it, because we need the Euler angles of the end effector, and we're gonna get those Euler angles from the rotation part of the homogeneous transformation matrix of the end effector. Okay, so here I'm defining the rotation matrix of the end effector, which is basically the top left 3 by 3 matrix of the homogeneous transformation matrix. And then here I'm using the function that I defined at the beginning to go from the rotation matrix to the Euler angles using as an argument the rotation matrix. So this will output roll pitch in yaw. And then we have our transformation matrix that maps from I don't remember if this is one or the other. Let me just check very quickly if I'm inverting it. Yes, so this maps from angular velocity to Euler angles. So this is the in our file. This is this.
No, I think it's the other way around. The T is from Euler rates to angular velocity, then you need to do the inverse, right?
Okay, but that's the notation. But the matrix that I'm writing in the code is this one directly. I'm quite sure of this. If you look at the, are you there, Michele? Do you have more questions?
Yes, I was just double checking this.
Yeah, maybe you can check the slides. And,
Yeah, I think is the other way around. Is the
so the matrix that I'm defining there. Let's see.
That's why you do the inverse then.
I'm not doing the inverse, I think.
Lineal give TA.
Ah, you're right. You're right. That's why that was my question. Yes, you're right. I didn't see that I was doing the inverse here, actually. Yes. Sorry, you're right. Sorry about that. So yes, this maps from Euler rates to angular velocity. Angular velocities, yes.
Yes.
So this is just defining this matrix here as we have in the lectures. So now here I'm just going to copy this. Okay. So here I'm just constructing the transformation matrix, which is basically I'm just stacking horizontally an identity matrix and a matrix of zeros, which is basically what we have on the top part of the transformation matrix. And then the horizontally stacking the matrix of zeros and our transformation matrix. And as the professor well noted, we take the inverse of this matrix, and this outputs the analytical Jacobian. And this is what we want to have. Okay, so let's save this, and then let's check here. So let's put our breakpoint here and run our debugger. I didn't put a difference, of course, because we cannot compare this yet because we don't have a function for the analytical Jacobian in Pinocchio. But what we can do is we're going to do this comparison when we solve the inverse kinematics. Okay, so let me stop the debugger. Now let's continue with the lab. So now we're gonna compute the numerical inverse kinematics. So what we're gonna do is follow the algorithm that the professor described in his lecture. And maybe I can make this a bit larger. So the inputs to our function are going to be the position in which we want to find the inverse kinematics, and an initial guess for the joints, the joint variables for the inverse kinematics. Then, if you recall, we're going to compute the delta Q value, which is basically obtained after solving optimization problem that the professor derived, which is defined as this. And then we will perform an update for the estimation of our Q. So our initial Q is 0, so we're going to update this Q0 with a step of this delta Q, which is the derivative of the delta Q, the approximate derivative. And then we have the two. Well, we're not going to do this, which is the step reduction, and then we're going to check what happens if we increase the value of the step. Okay, so let's go to the code. Kinding utils. You see that our inputs here are our value of P and our initial guess. And then let me remember how I did this. Okay, so first let's define a number of parameters. So this number of parameters are, so epsilon, it's basically the tolerance that we want for our algorithm to reach. So once the error is smaller or equal than this value, then we're happy with what comes out. Alpha is the size of the step that we're going to perform at each iteration. Gamma, it's something that we're going to use further in the evaluation to change the value of the step. Remember that the professor derived these equations to derive a variable step, because if you choose a too large step, you can get stuck in between iterations. Then we're initializing the variables of the errors. Then we have a lambda. This is going to be useful because we're going to see that for our inversion of the J transpose of our matrix, we're going to get singular matrices. So we're going to use a damped inversion with this lambda, which is very small, which is always it's always non-singular. This might like to move it here because this is also related to the step size. We're defining a maximum number of iterations. So if we get stuck in a value, we just stop the iterations, and then we say we didn't find a solution, or the solution that we found is not good enough according to the epsilon. We're initializing the number of iterations, and then we're initializing the value. I think I even don't use this variable. I think this is just legacy. So let's let me get my reminder. So I'm gonna go through the thing. Okay, so the first thing that we're doing, remember, if we look at so what do we need to compute this algorithm? First, we need to compute the analytic Jacobian. So we first compute you need to compute the geometric Jacobian, then we need to transform it into the analytic Jacobian. And then we need also the direct kinematics, because we need the position of the end effector. If you only want, for example, if you have a function that passes that returns multiple values, you can just ignore some values by putting an underscore. So here I'm just computing the Jacobian, and here I'm just computing the homogeneous transformation to the end effector. Then we compute the position of the end effector based on the direct kinematics, the rotation matrix. We need to do the, okay, something that is important that I needed to show you before, actually, is the shape of the geometry of the analytical Jacobian, because that's going to give us a bit of insight of what is our task space. So we can already say that we only have 4 joints, so we can only, the maximum number of task space variables that we can freely determine is it's 4. And then when we see the structure of the analytical Jacobian, we will see that the most convenient ones are the X, Y, and Z positions and the role of the end effector. So let's just visualize it just so that you can get a better idea. So I'm going to print it here. I'm going to debug. Let's see if I can click out. No, one terminal. Okay, let's give it a look like this. Because I cannot see the. Well, maybe I can run it and then it will throw me the error because there's nothing printing. Okay. Here it is. Make this a bit bigger. Okay. Well, this is just because of the position that we're choosing. But what I wanted to show you, this row, it's always going to be 0. If you perform the transformation by hand, the output of this is going to be 0. So basically what this is telling us is that you cannot set freely the value of the pitch of the end effector, and it kind of makes sense if we give a look to the. I don't have harvest running anymore. Let's see. Visualize. Okay. Okay. So it kind of makes sense if we look at our end effector, because let me move this. Okay. So let's visualize it like this. So role, if we look at our, again, we see that there are ones here that we can, basically this says that the angular velocities of joints 2, 3, and 4 can change the value of the role. So you can modify it. And if we look again at our end effector, we see that it's only axis of rotation is this one, right? Which corresponds to the roll axis of this one, of the end effector. So in the end, our task space is going to be X, Y, and Z, and the roll angle. Okay. So again, coming back to our analytical Jacobian, our inverse kinematics computation, we will see that our task space is going to be X, Y, and Z position and roll. So first I'm defining the position of the end effector, the rotation matrix, and then I'm finding the roll pitch yaw angles, and then I'm just getting the roll out of them. And then this gives me so here I'm computing it first for our initial value of the result of the inverse kinematic. So how are we initializing? So this is going to be the first iteration, and we say, okay, I need to compute the position, the task space variables for this specific result of the direct kinematic, of the inverse kinematics, and then we say, okay, I will compute the error of this. So this is the one that I'm getting, PE, which is the first approximation, and this is the one that I'm setting, which is the argument of the function. Then, using the previously computed function to get the transformation from geometric to analytic Jacobian, we compute the analytical Jacobian, and then we're going to take only the first 4 rows that correspond to the first 4 task space variables of the analytical Jacobian, right? Then here I'm just computing J transpose J, which is basically what we see here. So in this part, I'm breaking down the computation in small steps, because then I wanted to have like a more modular code and not have a large line doing the entire computation. So you have here J transpose J times, this is the definition of J transpose J, this is the inverse of J transpose J, this is P. Okay, now here, actually, let's remove this lambda, and then I'll continue, and then we'll come back to this. Then we have J transpose J, and then this P is just I'm just computing basically this whole thing. So this is P without the minus sign. So just J transpose J inverse times J transpose times the error that we're getting. So the error that we got here. Okay. And so this is what we get. And then we update our value of Q with, so we update the Q0 plus the delta Q that we just computed here times our time step, which is alpha. And then we define our Q1, our Q0 equal to Q1. And then we increase the iteration. So now I remove the lambda that I had here. So let's see what happens to the solution of our inverse kinematics. Okay. So I'm gonna put a breakpoint here. And am I already outputting what I want? Yes. Okay. Now let me change the values of the initial. Let me see what values do I have actually now in the initial values. So let's try to keep it like this. And let's see what happens. So let's run the debugger. And there was no error. So here we were lucky, and J transpose J existed. But in general, we would like to have, I had an example. Let's see if the example that I have here actually gives us a singular without the damped. No, it's the same. Okay. Oh no, but this is not the initialization actually. Wait, give me 1 second, because what am I using to initialize the inverse kinematics? This is the one that I'm using to initialize. Hopefully this will give us something bad. Okay. Let's start the debugger. Give us a little space. Okay, yes, I already had it here. So let's try a different initialization. Rerun. And let's see if it gives us. Nope. Well, it is safe. I couldn't manage to get the example where you get the singular matrix, but we're adding this damping here because this basically ensures. So you're basically to your J transpose J. Sometimes it's ill-conditioned. So sometimes you're very close to singular. So for example, one of the values of your J transpose J is getting one of the rows is getting close to all of its values being 0. So if you add this damp term of the identity, then you at least have a diagonal matrix going along the which you're sure that it's not singular. So you're just damping your transpose, and this works very well if you're dealing with a system that it's very close to to reaching those kind of, or if you really have a bad initialization. So, well, we computed our delta step, we computed our Q. So let's see now if our inverse kinematics function works, comparing it with Pinocchio. So here what I'm doing, so this is my initialization. So I'm trying to compute the inverse kinematics of this point. So I'm going to minus 0.5, minus 0.2 in X, in Y, and in Z, and then I'm trying to put the end effector roll orientation at 60 degrees. And the initial value for my, actually this is a bit confusing because it seems that it's also an angle, but I'm gonna leave it. But these are joint variables, basically, and basically this is the output of your inverse kinematics. Remember that for the inverse kinematics, we want to find the set of joint positions that give us a specific Cartesian position, well, a specific task space position. So in this case, it's an XYZ roll position. We want to find the values of Q1, Q2, and Q3, and Q4. And this is how we initialize it. So here's our inverse kinematic function. And so this is how we compute it. We just put the value of the task space, the initialization, and then to compare it, actually, we're going to compute the direct kinematics of the output of the inverse kinematics, just to compute the actual Cartesian position that is coming from the same. And hopefully this will give us the difference between the value that we introduce to the function and the value coming from the inverse kinematics. It's going to be equal to 0, plus the roll value actually as well. We're also getting the roll value from the direct kinematics. So let's run the debugger. Where did it stop? Ah, I put something here. What did I put here? How can I remove this? Let's just remove the line. I'm going to stop the debug. Okay, let's try again. Okay, now I run it. Where are my debugging variables? What is my error? Here it's showing me an error, which is, let me just check my inverse kinematics. Am I missing something? I will just copy paste again, just so that we can be efficient. Okay. Let's see if this doesn't complain. This is still giving me an error. Why? Am I not given the right values? Value error, shapes 461 not aligned.
Which line is it giving me the error? No. I'm sorry, guys. I am struggling a bit to find the error. What is it? I'm missing something.
Ah,
Tell me.
show me the code.
Yes.
No,
No.
seems okay.
Yeah, maybe I'm setting on the value that I'm sending, it's incorrect. Heck, no. 1, 2, 3, 4. No, that's fine. 1, 2, 3, 4. That's fine as well. The error is in the inverse kinematics function. Let's see that this. This. No.
Maybe you should kill there's some ROS master active in conflict. No.
No, because I'm not sending joint variables. There is one, but I'm not sending joint variables yet. What's happening? Hmm. Let me just see if I'm missing a step here. I'm not using this. Hmm. Ah. What? I think I know what it is. I'm not sure why it's giving me trouble now, but I think it's this. If I remove this, work. No, it's not this. It says here that the error is in this J bar transpose times J bar.
It looks okay.
Yeah, I don't know. I don't understand what's happening.
If you want, I can maybe share my screen.
I mean, I have the file here.
Yeah,
I mean, I will run it like this.
yeah. Don't.
Yeah,
waste
I
time.
would spend most time on this. Okay. So sorry for the hiccup. Let's now run this here. I'm using here because I'm running in my local PC, and I'm not using the virtual machine. I'm using the Docker, which is a container similar to a virtual machine, but it runs on your kernel. Let's see. Actually, here I'm printing the values. So let's see. Let's run the debugger here. So if we debug this, and we go back here, then I mean I'm doing exactly the same thing as there. Here, for example, here we were setting a value outside of the workspace of the robot. So one thing that I wanted to do before is that when you reach the maximum number of iterations, so we set a condition here for the error. So there are two conditions. One is that the error is, as long as the error is longer than epsilon, the epsilon that we set here, and the maximum and the iterations which we are adding at the end of each loop, it's smaller than the maximum number of iterations, just do your thing. If you reach the maximum number of iterations, then what's coming out here, it's going to tell you that the maximum number of iterations was reached and there was no solution. I mean, you didn't solve the problem. So just to verify this, what I'm saying here, here I'm printing the difference between the p variable and what's coming out of the direct kinematics using the output of the inverse kinematics. And here you see in the terminal, maybe it's too small, right? Let me see if I can change the size. I don't know. I don't want to waste too much time on looking how to change the size. So here you have the difference between the position that you wanted to get the inverse kinematics for and the actual result of the direct kinematics using the joint angles outputting of the inverse kinematics. So here you see that it's not zero. This is the text, so saying that it's not zero. So let's stop the debugging and let's change the value of our inverse kinematics. Okay. So, and actually, the solution that the numerical inverse kinematics throws is the one the closest to the workspace of the robot. So the value that it's outputting this, it's the one on the boundary of the workspace. Now let's do it for a value that it's within the workspace, and I'm gonna run the debugger. And then we see that the error is actually 0, 0, 0, 0. Okay. Then we proved our inverse kinematics function, but let's try something out. So okay, before doing that, let me comment this. And then we give a look at the output of the inverse kinematic function. So here I'm printing QL. Why isn't it printing it? Okay, so I'm gonna print it here. Okay. So let's print let's start the debugger. Rerun the debugger. And what we see here are the values of the coming out of the inverse kinematics of the joints. Now let's use our initial different initialization here. I'm gonna comment this one and copy it below. And now let's use the crazy value. Let's use let's say 3 times pi for initialization of our inverse. Actually, we can just use 5 here. Remember that these are the joint space variables, and let's see what comes out of this. Let's run the debugger. It's coming, it's throwing me the same value. Am I actually printing this? Let me just put the print QF. Okay. Okay, let's see. Okay, I know what was happening before. I'm gonna put my breakpoint here. I'm gonna remove this. Okay, let's see. Okay, this is the values that it's showing me. Now, let me see, because I wanted for it to wrap. Let's see, how can I make this so crazy? It's working really well. Much better than this afternoon. Okay, here you go, something that I wanted to see. So here, for example, you see that the output of the inverse kinematics, it's 10. And this means that actually that specific joint, it's gonna give 2 turns till it reaches the position. So we can have an equivalent position for the joint if we just unwrap it and put it within minus 2 pi and 2 pi. And I just implemented this at the very end of this function. This is just basically what it's doing is for each joint, while the value of Q0 is larger or equal than 2 pi, we subtract 2 pi. And this is just basically taking the joint, giving one circle around the joint. And in the opposite direction, if the variable is smaller than minus 2 pi, then we add 2 pi. And this way we take it. So when we'll see that during the simulation, actually it might be good to keep this in mind, because in the simulation you'll see the robot doing the 2 rotations. Okay, so let's look at the other thing that we want to do is actually okay, the other part of the I would like to do the simulation now today. So the other part of the inverse kinematics is actually to implement the variable step, and just think of limit cases in which if you don't implement a variable step, the iteration will bounce between the values. So let's just skip it for now. At least we now have a way to compute the inverse kinematics. And I'll figure out as well tomorrow, why isn't this working? Let me see if I just copy paste this solution. I can just continue on in the virtual machine. Let's see if this works. No, there's something wrong with a dimension. I'll figure out later. Probably I'm making a mistake outputting the Jacobian or something like that. So let's continue with the implementation that I have in my computer. So now we did the numerical inverse kinematic part. So now using this blocks, actually, what we're gonna do is that we wanna see the robot moving from one position to the other. So we need to define what's going to be in between these 2 positions. So for example, our robot, it's at position 0, 0, 0 in the joint. So it's basically stretched along the x-axis. And we want to take it to, I don't know, 1, 1, 1, and with an orientation of 60. So we need to solve the inverse kinematics, and then we need to find the joint trajectories for each of the joint variables. So a very simple way to do this is to use a fifth order polynomial. The professor talked a bit about them in one of the dynamics lectures. I don't recall which one. But basically, the idea is that you define the joint variable as a function of a polynomial of order 5 of order 5th, and then parameterizing time. So basically, the variable that we have, it's time, and then the idea is that you get also the derivative of this expression, which is you can easily obtain it analytically, and you also get the acceleration. And then once you have this, you can define initial conditions for the joints, initial and final conditions. So for example, in our case, the initial position of the joint is where we are starting the motion. The final position of the joint, it's the final position that we're going to get, and we're going to get the position of the joint through the inverse kinematics. And then we're going to set initial and final velocity to 0, initial and final accelerations to 0. So now we see that if we set initial and final velocity to 0 here, so let's say if we set these values to 0, and then we also know we can define also an initial and final time, which is the time that it's going to take to move from point A to B. We can define initial and final time. So we can set, let's say, a problem in which we have the initial conditions at time 0 and the final conditions at time f. And we can basically obtain these coefficients A0, A1, A2, A3, A4, and A5 by solving a system of equations of six equations. It's a linear system of equations. So this looks something like this, which is basically a matrix of 6 by 6, where 3 sets of equations correspond to initial conditions. So we replace this with the initial position of the joint, and this with 0. So for example, this is why our first row, it's 1, 0, 0, 0, 0, 0, because all of the variables are multiplied by time, but the initial time is 0. So what's left is 1 here. So I'm just building this with a matrix. The second one corresponds to the final position, so the final time. So we have the final time here, and it's just replacing those values, and then I construct the matrix like this. And then in the end, we solve the system of equations by defining, we define this vector, the vector for the polynomial, which is just the initial and final positions given by the initial and final positions, the initial and final velocities, which are 0, and the initial and final accelerations, which are 0 as well. And then we solve this by inverting this matrix and multiplying it by the vector. And then we get the coefficients A0, A1, A2, A3, A4, and A5. So the output is this this set of coefficients. So now what this is not working, I remember. Maybe I'll try to fix this now. Okay, never mind. So let's go here. So let's go to our L3 kinematics file. So in here, I'm starting a while loop. And basically what this while loop is doing, it's running. So what it's doing is it's checking the difference between the actual value of the position and the final value of the position obtained through the inverse kinematics, which is this QF, okay? So first, we define our polynomial trajectory. So first, we need to get the coefficients from our function that I just explained. And remember the arguments. So for example, here it's the time that you want the motion to take. So here is 3 seconds. the initial value of the joints, which come from their configuration file, and the final value of the joints. And then with that, we compute the output of this. It's a vector A that contains the coefficients for our polynomial trajectory. Okay. This is not important. This is just logging for plotting. And here we're just increasing the time by a delta t, which is given. Let me stop this. In our conf file, in this case, it's 1 millisecond or step. And then we're basically finding the values of Q given the polynomial trajectory. This is defining the values of Q given the polynomial trajectory. And then this is, remember our publisher, this is just publishing to the joint state in the, that is going to be received by Arvis. Okay. So let's run this and see what it does. Okay. So I'm going to run this. I had already run it. Sorry. Okay, so you saw here that the robot did a series of loops, and this is because one of the outputs of the inverse kinematics, it's 10. So let me slow it down a bit so that you can see better. We can slow it down by, in our config file, we get this slow factor, and then we put it to 10. Okay. And then here we go. Here you see that the robot is reaching, it's doing these loops because the output of the inverse kinematics, it's 10. So let's put again our wrapping function. Here, which we commented out here. Oh. And let's see what our simulation does. Again. It did one loop only, but still, it's not a very good trajectory, at least. But this is due to the initialization that we're using. Actually, if you remember well, I was playing around with the values of the initialization to generate this behavior. So
set the good one. Set the nice one.
Yeah. That's what I'm going to do. Here. So let's put the initialization here. And again. Here you see a much nicer motion. Now, let me open the the description just to finish today's session. And this is the extra question that we would like to ask you for if you want to get the log. And so, as you saw, the value of the trajectory, it's really prone to that values due to bad initializations. If you change your initialization of the inverse kinematics, then your trajectory is going to be very bad. And also, a consequence of the fact that we're using so setting your trajectory in terms of the polynomial, it's easy and it's fast to compute. But the problem is that you don't know exactly what's happening in between the motion. You don't have control. You're basically not controlling what's happening in between the 2 points. So you're just giving it your inverse kinematics to solve the problem as it likes, and then it performs the motion as it will. So that's why you get these trajectories that might collide with itself. So a different approach that you can take is that instead of setting a polynomial trajectory for the joints, you get the 2 points, your initial and final point, and then you parameterize. Let's say you, for example, you connect them with a line, with the equation of a line, and then you can actually get the parametric equations with respect to time of this line, the parametric equations which is of time, right? So then you would have a value for each time step that we have in our simulation. So this value of t would go into a function that would be the parameterized function of the line equation. Let's say, so it would be 3 equations x, y, and z, which the independent variable is time, and you would have a value for this. And then the idea is that you solve for each of these values in Cartesian space the inverse kinematics as you move along. So if you want to get the loading, you need to implement this. This is described in the file. If it is not very clear, you can also send us an email, and then in case you have questions. And this is the load exercise for this lab.
Yeah, sorry, Claudio, I just want to do an observation. So remember what was our last comment at the lecture is that we can initialize each time step with the previous solution. So this way,
Yes.
from a Cartesian trajectory, we can reinitialize at each sample time the inverse kinematics with the previous joint configuration from the previous solution, and this way we don't have this bad trajectory that we end up previously. So
so basically, what just to add to this, what you're enforcing is that the solution of your inverse kinematic optimization is going to be close to the previous solution of your inverse kinematic. So you're not going to do this crazy motion, and as long as you design a good trajectory, then it's fine.
Yes, exactly. Well, then, here in essence, you solve it once, and then you try to connect the actual joint position with this in some way with a polynomial to the solution that you found.
Yeah, and just as a final comment related to the inverse kinematics. So if you recall, when we're solving the inverse kinematics, we're solving an unconstrained optimization problem, and this means that there are no limitations on what values the solution can take, except for the ones that take you to the cost function. But some interesting thing is that if you set up a constrained optimization problem, you can actually set, for example, joint limits. So for example, if you have a robot that has a mechanical joint limit that you cannot rotate, if you see a robot can rotate all 360 degrees, you can set a joint limit, and you can set up an optimization problem with your joint variables already defined, and the output of your inverse kinematics would already be feasible for those joint limits. And usually what you use to solve this kind of problem, it's a quadratic program because you have linear constraints and a quadratic cost. So obviously the function might be a bit different, but if you want to try, this is not for the Lode or anything. There's actually a functionality to compute to solve QPs in Locosim. So if you want to try it, be my guest. And that's all for today. If you have any questions or comments regarding the lecture the session so far, feel free to send me an email or ask me now. Otherwise, see you tomorrow.
Maybe I have an observation.
Yes.
I'm not sure the problem that we got on the the transpose multiplied by the Jacobian. It seems it was like a three-dimensional matrix. I don't know, something like that.
Let me check.
Maybe when you initialized that there was another bracket. I'm not sure.
Let me check. Maybe
But
you're
it
right.
could be just
Yeah, maybe. I mean, maybe you're right. Let me check.
because
It doesn't seem, but I mean, I'll check it and I'll bring the
yeah,
correction tomorrow. Where we'll come back to this and I'll show you. Okay.
Yes, I also added to the PDF of the intro slides that you prepared to presented today a drawing of the robot with the frames and the links highlighted, such that you can better orient yourself into the kinematics of this robot. Unfortunately, that was an example where we the guys that the manufacturer of the UR4 robot, which is actually a reduced version on a UR5 robot, they didn't follow the convention of setting the z-axis of each joint align with the joint axis, so with the moving axis. So this is just to show that in the URDF you have the freedom to do whatever you want, and in that case they didn't follow this convention we presented at the lecture. So I found useful to prepare a slide just to show you the frames.
Okay. Thanks.
Okay,
Okay. Then see you all tomorrow.
see you tomorrow.
See you.